Okay. So one thing, I think I'm going to move the due date to the homework to today. I'm kidding. I'll move the due date to the homework to actually Tuesday, to give you a little more time to tinker with some of this stuff here. Okay, so let's put that down. So homework. We're up to homework 8. I think homework 8, right? So homework 8 is due on next week. Then I give you a little chance to kind of tinker with some of the stuff that we're talking about. And what I want to do is I want to go over some of the ideas we did last time. Again, a lot of you are material science or electrical engineering or ceramics or whatever, or maybe taking more physics. And at some point, you just have to understand this stuff. You'll go into more depth. This is just kind of a little beginning introduction to it. So we talked about semiconductors. And let me give you a little commercial. In the spring of next year, if you take modern physics, I'll go into more details about what these things are. Right now, I'm just going to give you the two of them. We said that there's silica and germanium. These are two of the classical ones. We said that they actually form 4 bonds. So if I do the 2-dimensional representation of this, I have something that I'll just use silicon. There's 4 outer electrons. Those 4 outer electrons are called valence electrons. And what happens is I can have another silicon coming in here, and then another silicon can hop over here, and another silicon can hop over here, and then so on and so forth, and this is what you have. That's fine. Now we said what is going to be interesting is if we start putting impurities in. And when you start putting impurities into these things, this is called doping. So if you look at the column here, these are on column 4, like this. What you're going to do, we're going to actually add impurities from column 3 and from column 5. We're going to have impurities. From 3 and 5. We said the impurities from column 3, they are going to have 3 valence electrons. Okay, we said an example, this would be, we said aluminum. They're going to have 3 valence electrons. And then the ones from over here, they're going to have actually 5 valence electrons. And we said an example we took to be arsenic. We said we have arsenic here, so there's 4, then there's a 5th one here, like that. Now, what we can do is that when we make these things here, and again, the way these are often made, there's a whole bunch of ways, but one of the ways that was made with vapor deposition. You basically have some material silica here, and you have a vapor, and that vapor then deposits on the substrate, and you kind of grow the semiconductor this way. When that vapor, you can also put in vapor of either aluminum. People often use boron as well, or you can put in a vapor here of arsenic. And so what I could do is I could put in this impurity or this impurity here.
Can you add impurities from any well? From any well that doesn't have 4 valences?
You can put in any type of impurity you want. Now, what's going to happen though, that's going to go into its crystal structure. So not everything is going to fit into the crystal structure well. So you want something that's going to fit into the crystal structure well. And with these being really close to this on either side, this and this are going to fit into the crystal structure here really well. So that's why you would do something like that. Okay. This is a whole art form in what you do. This is just your little beginning snippet of it. It's really you can spend your whole life, and people do spend their whole life working on these systems. And so let's say we put in aluminum. So if we put in aluminum here, what's going to happen here is I'd have the aluminum here like this. I have another S on here like that. Here. Then I can have silica here. Here. What's going to happen here is that I have a little hole. We'll put a little circle here. That little circle here, this is the vacancy. And it looks like a hole. And so when I start putting these things here, what's going to happen here, we're going to call these P-type semiconductors. So this would be a P-type semiconductor. So anything made, basically, if I put in the impurities from column 3 are going to be P-type. So boron, aluminum, they're kind of common things you could put in here. Okay. And we said that if we put an electric field on this, if I have an electric field like this. Okay, if I'm a little electron here, how am I gonna move? What's gonna be the force on me? It's gonna be going to the right, so let's say I'll take this one here. So this one here can hop in here and then fill this hole here, so I could then have that filled, but then what does that leave here? That then leaves a vacancy. And then what happens? Well, maybe this electron here is gonna then fill this, so that's gonna be filled, and then that leaves a vacancy here. So what is this looking like? This hole is actually moving this way. If that hole is moving that way, what do we say? It's gonna look like a positive charge moving, and so we actually call that a hole. So these p-type semiconductors here, what's gonna be the main thing conducting here are gonna be holes. Okay, that makes sense? And we call those p-types. Now, since this actually accepts the electron, what we do, these are often called acceptors. So often another name for these p-type, the elements here, these are often called acceptors. Because they accept electrons. So here element accepts the electron. Okay, that's another name. I'm just going to call them p-type. Now we said what else? Well, when I have that substrate of silica and I have that silica vapor, I could just as well put in basically, I could add a vapor from column 5, like arsenic. What's going to happen in that case? We're going to draw the same picture. Then what happens? Well, I could have another silica here. And then I could put my arsenic here. That has an extra electron, let's say here. Then I could add more silica here. Here, here. And I could add another silica here. And I can have a silica here. And so on and so forth. So what happens here is now if I have an electric field, well, let's see this guy. So here's my extra electron, right? So that means you can't see where I have an extra electron. I'll put my silica up here, so I have another electron here, here. So my extra electron is here. Now, if I have an electric field on this, and this is my E, what's going to happen to this extra electron? There's going to be a force on it, and that extra electron is going to move this way here. So in this case here, negative charge. Moves this way. And since we're getting actually an extra electron here, we call this N-type. These are going to be called N-type semiconductors. And since these are donating an electron, because they have an extra electron to donate, we often call these donors. So these are also called donors. Because five elements. Contribute an extra electron. Okay, that's what we have here. Now we said what's going to be interesting here is basically when I put the p-type and the n-type together. So we said what could we do? We have basically our silica substrate. We have our silica vapor. We add aluminum to that, so we're going to start growing a p-type semiconductor. Then we stop putting in the aluminum vapor, and then we add arsenic vapor, and then we start growing an n-type semiconductor up here. So what we're going to have in that case is what's going to give rise to what's called a p-n junction. So I'm going to draw it this way here. So here's my silica. So this would be my p-type here like that. And then I'm going to have my n-type here. So let's draw a couple of these here. Let's put aluminum here. Silica here. Let's put a bit of silica here. Here. Put aluminum here. back, what I'm gonna have here. Is I'm gonna have a vacancy here and a vacancy here. But on this side, I'm gonna have the arsenic. I'll have my arsenic here. Silicate here. This will be my extra electron here. I can have my other arsenic here. Over here. In this case here, I have my extra electron here, extra electron here. So these are extra electrons. Here, these are my vacancies. Yeah. Now, what did we say is going to happen? Okay, well, let's put in a little more details. There's something called diffusion. What does diffusion mean? So let's say I have a thing of water, and I take a thing of red food coloring. I put a drop in there. What's going to happen? Well, those red molecules from the food coloring are going to what? They're going to be moving around because there's thermal motion, and they're going to bump into other things. And by thermal motion, that red dye kind of spreads throughout the whole region there, and that's referred to as diffusion. Well, what's going to happen here? Well, these electrons here in these holes here, they were also going to, there's going to be thermal motion there. They're going to kind of move around. And so what's going to happen is that the electrons can start drifting over here, the holes can start drifting over here. And left to its own accord, what's going to happen is that basically you have kind of the holes and the electrons being all over the place uniformly. So something unique happens. So what happens is by diffusion, some electrons here. I'm going to hop over, and I'll just put them onto it in black. The electrons here are going to hop over this way here. Electrons over here, we're going to hop over here. Now, what happens here is that these atoms are electrically neutral. So what's going to happen, these electrons start acquiring electric charge here. So they're going to develop a negative charge here. But the electrons like arsenic over here are electrically neutral too. So if they lose an electron, they're going to get a positive charge because of the nucleus here. So what's going to start happening here is I'm going to start getting negative charge building up on this side due to the electrons being here. Okay, so I'm going to get negative charge building up here. And since I'm losing the electrons on this side here, and the arsenics are electrically neutral, this is going to start getting a positive charge. That makes sense? So this region here is going to have an electric field going this way. So this is going to be the electric field here. And that's entirely due to the fact that these electrons over here are going to diffuse over here. These holes here are going to then diffuse over here on this side. That makes sense? Now, why do I not have to worry about all the electrons here just continuing to diffuse over here? Let's say you're a little electron here, now you try to diffuse over here. If you're a little electron here, what's going to happen to you? The electric field from here is going this way. What's going to happen? Well, there's going to be a force on you moving you back this way here. So the reason why all the electrons here don't kind of start diffusing over here, and likewise the holes over here diffuse over here, is because of this electric field that develops when these charges moving over here. That makes sense? Now, just out of curiosity, you can see something here. What happens when I have a positive charge here and a negative charge here? Is that called something else from what we've been studying? Not yet. Connected with that, a capacitance. So you're actually developing a little capacitance here. So often when you study these things here, you're going to actually talk about capacitance here, and when you do it in more detail. And not just that, if I have positive charge here, negative charge here, electric field going that way, what else is going to be here? Let's say maybe you had a S2 on this. You'd also have a voltage difference here. Okay, so you'd have a voltage difference here. If this is a silica semiconductor, the voltage difference here is 0.7 volts. If it's germanium, the voltage difference here from this right here is actually going to be 0.5 volts. Okay, kind of neat. Okay. Now, this right here, this region in between, Basically, all the holes have been filled with electrons here. There's nothing, the charges can't easily move. This region here, it's called the depletion region. What it means here is that there's really no more charges that can move easily here. Okay, there's thermal motion can cause some things here, but for the most part, there's no free charge that can move in this region. Now, what's going to be interesting here is if we put an electric field on this. So what I want to do is say, what happens if we put an electric field on this? So what happens if we place an electric field across the PN junction? This thing right here, this whole combination here, where you have the P connected to the end here, this whole thing here, this is called a PN junction. So this is what happens here. So I'm going to draw this here. So here's my P type, and here's my N type. And what I'm going to do is I'm going to put a battery like this. That's my battery like this. So I want to draw this region here. So in this region here, what's going to happen here? I have this little depletion region. So here's my depletion region. This has a negative charge over here and a positive charge over here. So that has that little electric field going. Okay. Now, if I have a battery hooked up this way here, which way is the electric field going to go from this battery to this material? That's right. So like this, right? This is positive and negative, so the electric field is going to go this way. So the electric field from the battery is going like this. So this is the E field. From the battery. Now, what do you know about the E field from the battery and the E field that's been induced by this charge migration here? They are in the same direction. Okay. And what this is going to result in, this is actually going to result in that the depletion region actually getting bigger. I want to show you how that works. So this is N type, so you have a little free electron, you have some free electrons here. Okay, if you're a little free electron from the N type, which way are you going to move? You're going to go this way here, hop over here, and then go on this side here, then end up here. So what's going to happen? This side here is going to start losing electrons going across here. They're going to start coming on this side here. What's going to happen here? This side loses electrons, it becomes more positive. So this region here kind of moves out this way. It's bigger. The electrons are getting over here, and they'll eventually migrate over to here. It's going to go like that. That depletion region now becomes larger. So the depletion region. Increases. We said in this depletion region, there are no real charge carriers. And what that means here is that since charge can't easily flow here because there are no charge carriers, the current's going to go to zero or become very, very small. So what's going to happen here is that any electrons over here can't easily go through this depletion region because basically all the vacancies have been filled. There's really no charge carriers or to go through. So that you have some current going through there, but remarkably little. So what's going to happen is that if you try to make the current go basically this direction here, okay, it's not going to work. Okay, we're going to have very limited current. That makes sense? So there's going to be little current flowing through the device.
Like the region to increase one of the neighbors from the battery.
Yeah, if you make this a stronger and stronger voltage, this will happen more and more and more. Yeah. It'll go get bigger and bigger. Okay. Now, let's connect the battery in an opposite direction. So now I'm gonna have this exact same picture. I'll draw this out here. So here's my P type, here's my N type. I have, again, here's my load depletion region. So I have the negative charge over here, positive charge over here, and then my electric field. Now let's connect the battery in a different direction. Now let's connect it like this. Now set this. Okay. So what does this look like here? How would the electric field go in this region here? Yeah, it's going to be going like this. So this right here, this is the E field associated with the battery. Okay. So you can see what's going to happen physically here is that we said that for a silica semiconductor, this is 0.7 volts. Well, if this battery here has a voltage greater than 0.7 volts, you're going to be able to take electrons here and actually from this side here and actually kick them across this barrier, and then they're going to move. So what's going to happen here is that if the electric field goes this way, this is from the battery, the electric field from the migration of the charges here are going this way. Those electric fields are going in opposite directions, and so this electric field gets weaker here. And so what's going to happen then to our depletion region? It's actually going to get a lot smaller. So what's going to happen here is that, and you can kind of see this here. So what's going to happen here, the electrons here on this side here, there's going to be a force on them this way. If the electrons then move over here and then come over on this side here, if I'm losing electrons on this side, that means that this side here starts moving this way. And then if the electrons come here, then go to the positive side, now this will become neutral, so that side starts coming in like this. What's going to happen here is that this region here gets smaller. Now I just draw it in like this. Okay. So in this case here, the depletion region. It's also called the depletion layer. Okay, it's smaller. So what happens here, if you're a little electron here, you want to go this way here. But what we said here is that electrons can't easily go through that depletion region because there's no charge carriers. But if that's getting really, really thin, what can happen here is that there's going to be basically a velocity of these particles coming this way. And if this is thin enough, these electrons here can kind of punch through that region here, even if there's no charge carrier. And so now I can actually have a nice current flow this way. So what's going to happen in this configuration here, current can flow when the battery is connected like this. So the positive side here, the battery is connected to the P type here. The negative side of the battery is connected to the negative side here. You can have current flowing. This is called forward bias. So the battery is connected like this. It is called forward bias. You can have current flowing. When the battery is connected like this, you have very little current flowing. This is called reverse bias. So the battery over here, when the battery, let's see if I'm so focused. I am so focused. Ooh. When the battery is connected like this, it is called reverse bias. And this device here, where you have the PN junction, this is called a diode. So this device with a single PN junction is called a diode. Okay, and the electrical symbol for this, so what does this mean? This is going to allow current to flow in one direction easily. And since current can flow in one direction easily, we're going to have basically a little arrow there. So that's a symbol for a diode. This is the electrical symbol for the diode. Hey, which way do you think current's going to be able to flow if that's my symbol? Yeah, it's going to flow in the direction of the arrow. The current can flow that way. So how would you want to have current flowing here? If this is positive here, if I make this a high voltage, if I make that a low voltage, then this is going to allow current to flow here. This is forward biased. If I flip it and do this, right, this negative, this positive here, this is called reverse bias. And there's a little current flowing that way. Okay. When we get to AC circuits, I'm going to show you how to convert AC to DC. And the way we're going to convert AC to DC is basically with the diode. We're going to make what's called a half-wave rectifier. Actually, it's going to be called a full-wave rectifier. That makes sense? And that's a little more detailed than is normally done in this course. But again, there's enough engineers here, and I think there's when they're all here, that I thought it's time well spent. You're going to take courses on this, and at least you have seen it once. So then when your professors come and talk about it in more detail, you can go, oh, I think I understand a little better what's going on. Okay. Now, I want to say one more thing. You're going to see this in the homework. So in the homework 8, you are going to calculate. Okay, is anyone have a copy of the homework? This is going to be a number 2. You're going to calculate the drift velocity of you're going to calculate microscopic properties of metals. So for example, here, this case here, so in homework 8, question 2. Okay, you're gonna have silver. So here's silver, and it has a density of 1.5 grams per cubic centimeter here, and a resistivity of 1.59 times 10 to the -8 ohms per meter here. And you're going to have to find, you will need to find the number density of electrons. Okay. This will be here. So I don't want to do this one for you, so let me take a different line. So let's say we take gold. And hopefully this book here has gold in it. Are you kidding me? Check alternates in a periodic table. Is it the only physics book in the world that doesn't have a periodic table? Okay, so this is the only physics book in the world that doesn't have a periodic table. Can't remember which one I looked at the other day, which had the periodic table. Okay, fine, we'll just deal with this. Okay, so, how would you then go about calculating the number density of electrons here? If let's say you have some density, it doesn't matter what it is. Okay, and I make something up. Like, take an example here. Okay, some unknown metal has a density of 20 grams per cubic centimeter. Okay. If each atom contributes 2 free electrons. Let's say 3 free electrons. 3 free electrons. What is the number density of free electrons? Okay, you tell me how to do that. And also you have the number of, and let's say you have 400 grams of material. 400 grams of the material has a mass density of 20 grams per cubic centimeter. And each atom gives up 3 electrons. What would be the number density of free electrons? Give you a hint, you could do it from chemistry. What do you do? Okay. How many, first of all, you'd have to ask is how many how many atoms would you have? Well, 3. Well, okay. So I'll give you a sample of something. And I want you to tell me how many atoms there are. What would you do? This is why I need the periodic table on some stuff. What can you get on the periodic table? Yeah, you get the grams per mole. What is that called? It's called the molecular mass. Okay, so you'd have the molecular mass, that's often a capital M. So, if we had the molecular mass, okay, which is gonna be what, that's capital M. Remember, the capital M is the number of grams per mole. Yeah. Mhm. And what do we know about a mole? One mole is 6.02 times 10 to the. Oh, you get voted off the island here, okay? Oh, you get voted off the island, okay? Oh, you're all off the island, no, that's okay, I retract, no, none of you get A's in the class, sorry about that. 23 atoms. Right. So one mole is 6.02 times 10 to the 23 atoms, it's Avogadro's number. Okay? So what do we have here? If I had 400 grams. Okay. What would I do? How many moles would I have? I'm gonna make this up. Let's say in this example here, let's say M is gonna be I'm just making this up. Let's say 30 grams per mole. I'm just making this up. What would I then do? Yeah, if I were to take this here, and if I were to say then, if I were to say that this is gonna be 30 grams per mole. Okay, what do the moles do? They flip up, so this is what a mole is this. Right? And so what would that give me then? No, I should have really taken 40. So this is gonna be what? So this is gonna be 40 over 3 moles. Okay. So what? We get then the number of particles, atoms. Right. Let me say 1 mole. The 6.02 times 10 to the 23 atoms. Here. So this would be 43, 6.02 times 10 to the 23 atoms. This would be the number of atoms here. So how many free electrons would I be given up in the sample here? Yeah, we said 1 atom, I just made this up. We said it's contributing 3 free electrons. So I take this number here and multiply it by 3, and then that would be the number of free electrons I'm getting. Okay. So take 3 and times the number of electrons here. Okay. This would equal the number of free electrons. Okay. So what I do here, I have this 40 over 3, 6.2, 7 to 23rd. There's 3 here, they would cancel this, so this would be 40 from 6.02 times 10 to the minus 23 free electrons. Now, if I wanted the number density, then what would I have to do? Now, how do we always define a density? It's the amount of whatever per unit volume. So what do you have to do to this? We have to multiply this by or I'm sorry, we have to divide this by the volume. Okay, that makes sense? Any questions with that? So if we divide this by the volume. This would equal the number, I'll call this N sub E, which is going to be the number density of electrons. Okay. Now, what did we have in this case here? We had this here. So how on earth would I get the volume then for this? How big is my sample?
Mass over.
Yeah, if I have the mass here. And I know that this, if I take this mass over the volume here, it has to equal this, I can solve for the volume, and that's how I can get the volume. So I can find the number density. That makes sense? Now, so there's that part. Now, how do I then find all these other atomic properties? So let's do a little review of what we did a long time ago. This is probably, well, this is at the beginning of when we started circuits. So this is kind of an old memory. So how? So let's review the microscopic theory. Resistance. So what did we say causes resistance in the first place? The electrons, right? You have to have a material. Here's our material. Put an electric field here like this. If you're a little electron, there's gonna be a force on you going this way. What are you gonna do? You're gonna bump into the atoms here. So here's a little atom here. Here's an atom. Here's an atom. Here's an atom. There's all these atoms. You can imagine that these are all connected by springs like this. So what's gonna happen? You're gonna bump into here. You're gonna get this guy vibrating. Then you're gonna kind of recoil. Then you're gonna go this way here. You're gonna bump into this guy here. This is gonna bump into all these things here. That's what microscopically causes resistance. Now, how did we go about analyzing this? We looked at the force on this guy. We said if you're a little electron here, there's a force on you. We said that this force is given by Q times Z. Right? We know that the force also equals ma. So it said the acceleration for this guy is QE over m. Okay? We said, well, let's imagine this electron's initially at rest, and it starts moving, so we could say that this velocity is this v naught plus at. I'm going to assume the same is a constant, so I can use these equations here. This is going to say 0, so I'm going to say that this v here is approximately this a times t. So it's going to be this approximately qm e over t. And then what do we call this value right here? We call this here the time it takes to collide with something. We call that basically the collision time tau. So we call the collision time tau. So that's going to be related to basically how long it takes to make a collision. That makes sense? So we wrote this as this v approximately this qm e over tau. And this right here, this we call the drift loss. Now, what else did we do here? It said the following. We defined something called the current density, J. Okay. This is our current density. What did we say that current density is? By definition, it's badly named. Again, a density is always a what? It's stuff over volume. This is badly named. So this is gonna be stuff, in this case, charge, right? In particular, moving charge, so in other words, current. So it's gonna be the current moving through this wire divided by the cross-sectional area. It's badly named. Okay, this is gonna be by definition I over A. This is a cross-sectional area. So this J here is gonna be what? What's our definition of I? Always EQDT. I didn't put in deltas for no good reason. I could just do that. So this is going to be our delta Q over delta T. And so we looked at this little section here, our little wire here. And I looked at this little section here. I called this here delta X. This section here is A. And let's say that the number of electrons here, the number of electrons per unit volume. In other words, this is our charge density. This is going to be our number density of electrons. Okay. Well, what is this going to be? This delta Q here is going to be the charge of one charge. Okay. Times basically the number density of electrons here. I'm going to call this delta V. Okay, so this right here, this is my delta. This is my delta Q here, like that. And I'm going to take this, and now I need the volume of this. What did we say the volume of this guy is? Right. So this is this. Okay, I'm sorry. This guy right here. This is going to be my velocity. This is going to be my charge density. Pockets against me. Charge density of electrons. So you take the charge density times the volume, which is what again? A times delta X. And here's an A down here. So this A is this A. This is my volume. The A's cancel here. The delta X over delta T is my velocity here, V. This J here is my Q, N, E, V. And I take my V here, and I pop it into here. So this gives me that this J. So that Q combines with this Q. This gives me Q squared M. Here's my N sub E. Okay. Here's my V. And I'm going to take that electric field, and the tau is here as well. Here's my tau. And then here's my E. And what did we call this whole mess here? That whole mess in front of there was called the conductivity sigma. This is my sigma. Now, how is sigma related to resistivity? Oh, the resistivity is 1 over rho. So in this problem here, I give you the resistivity. The reciprocal of this is equal to sigma. Okay. If you come over here, actually, where's my you can actually, that means you know what the sigma is. There's enough information in there that you can actually kind of back calculate what some of these values are here. So what you're gonna have to do, you're gonna have to use this equation, this equation, and all that stuff for the chemistry part, and you can basically fill everything in. It's a really gigantic plug-and chug problem. None of it's hard, but it is a really, really large, gigantic plug-and chug problem. The other thing you're going to need to know here is that recall the resistivity is the resistance of a section of wire is rho, and the length of the wire over the area here. If I give you a cube, what is the area? A squared. So this is going to be rho. This is going to be L over. It's going to be L squared. So this is my R. And this gets here. My R is equal to rho over L. Okay. So what you're going to be able to do, you're going to be able to find R. You're going to know the voltage. That'll give you the current. From the current here, you divide through by the area here. The area. That'll give you the J, and then your J then is going to be the guy here, and you're going to back calculate. Okay, none of it's hard, but it will go on and on and on for plug-in checking and stuff. Okay? Okay, it looks like I killed you all. Okay. Have a good weekend.